Section 5.5, example 19, convergence of alternating series. So an alternating series, it's just like a plus minus series. So for, in this case, for even numbers, it's positive. For odd, or for odd numbers, it's positive. For even numbers, it's negative. So like it still converges, it still could converge, because if we look at values on a number line, we could go up to here for the first sequence, back this way for the second sequence, up here for the third, fourth, and notice how these values get smaller and smaller until they converge to one single entity. So with alternating series, they still could possibly converge or diverge just because of that. So here we have this, and here they want us to apply the, well, there's an alternating series test where with an alternating series, it has to satisfy two conditions. So the first condition, we look at the n plus 1th term. So we look at b sub n plus 1, that should be less than or equal to b sub n for all of the values. And b sub n is identified kind of like the absolute value of the alternating series, but we have to satisfy that. And once we've satisfied that, then we could look at the limit as n approaches infinity of b sub n. And if it equals 0, then it converges. But if any of those are not satisfied, then it doesn't converge. And we're looking at the sequence without it alternating. So in this case, b sub n, it's not going to be all of this here. B sub n is only going to be this value here. So b sub n is going to be 1 over n squared. And we're going to compare that to b sub n plus 1. So b sub n plus 1 is going to be n plus 1 squared, which, remember, if the denominator or larger denominators mean smaller numbers, so larger denominators mean smaller numbers, that tells us that n plus 1 squared is definitely a larger denominator. So that one's going to be smaller than just the 1 over n squared. So condition 1 is satisfied. Now that condition 1 is satisfied, we're going to go over to condition 2. We're going to take the limit as n approaches infinity of b sub n. If this is equal to 0, then it converges. If it's not, then it diverges, or we'll come to that when, or we'll answer that when we come to it. But here we're looking at the limit as n approaches infinity of b sub n. So 1 over n squared. And 1 over n squared ends up being just 0. So this converges to 0. So because it converges to 0, and because we satisfied the previous one where b sub n plus 1 is smaller than b sub n, we have just proven that this series converges. So converges. So a sub n converges. The entire series converges. There we go for that one. Let's look at part B. So for part B, we're doing the same thing. We're going to first look for b sub n. So b sub n is just our sequence, or I'm sorry, our series without the alternating part. So b sub n is going to be n over n plus 1. And we're going to compare that to b sub n plus 1. So the next term. So we have n plus 1 over n plus 1 plus 1 is going to be n plus 2. And with this one, I feel like it eventually goes to 0, but let's do, so this one's kind of inconclusive at the moment. We're going to ignore it. Let's look at the second condition. We're going to do a little pause. let's see if the limit tells us anything. So the limit as n approaches infinity of b sub n, so n plus 1 in the denominator, n in the numerator. Let's multiply the top and bottom by n, or 1 over n. So that's going to be 1 over 1 plus 1 over n, which equals 1. Ooh, since this one equals 1 and does not equal 0, so this does not equal 0, we cannot say that it converges or diverges. What we're going to have to say is that it's inconclusive. And because it's inconclusive, we have to do further tests, but at this point, we don't have much other than just them. And there we go. There's example 19. If you have any questions, please feel free to ask. Otherwise, bye.